Okay, we're going to be doing chapter 14, which has to do with acids and bases. It uses some equilibrium from the last chapter. This is definitely the longest chapter that we have this semester, and probably one of the hardest when we get into salts and things like that. So take your time, read it maybe more than once, and listen carefully. All right, so I'm sure everybody's heard of acids and bases before. And probably what are some of the things that you know about acids and bases? Well, or you may or may not know it, but acids tend to be sour. Bases tend to be bitter. If you think about, your fruit juices are sour. Those are acids. Bases, like aspirin happens to be a base. Soap, something that's got that bitter taste. We also know that acids and bases change colors with indicators. Indicators are large molecules that, whether they have the hydrogen, well, we'll talk about it more, they can change colors depending on if they're in an acid or a base. For example, phenolphthalein is colorless in an acid but turns pink in a base, and litmus turns blue in a base and turns red in an acid. And another thing about acids and bases is that they neutralize each other. Okay, so we're gonna look at two definitions of acids and bases in this chapter. The first one is called the Arrhenius concept, which is kind of the earliest one and probably the one that you're most think of mostly. And then we're also going to talk about the Bronsted-Lowry concept, or the Bronsted, sometimes Lowry gets dropped, the Bronsted-Lowry idea of what is an acid and base, which is more encompassing and a better definition of acids and bases. So you may or may not remember back in chapter 4, we talked very briefly about acids and bases, and now we're going to get much more into detail in this chapter. All right, so according to Arrhenius, who was a scientist way back when, an acid is something that, when dissolved in water, increases the concentration of H+. Probably that's what you think of it most often as H+. And we'll talk about it in a minute. If you take an H2O and you add an H+, then you have H3O+. And this is called the hydronium ion. So a lot of times H3O+ and H+ are interchangeable. Because technically an H+ can't exist by itself. It usually gloms onto some water in aqueous solution. So this is probably H3O+ is a more proper way of saying it. So acids, when dissolved in water, increase the H+ concentration. Yep, so like I said, often they're interchangeable. So usually probably I write H3O+, sometimes I'll write H+. Just keep in mind that they basically, in this in this idea of acids and bases, they mean the same thing. So yeah, here's an example. Technically, actually, an H+ is bonded to, in this case, 3 water molecules. So even 1 water molecule with an H+ on it is probably a little bit too small to keep that concentrated H+. But so they tend, because of hydrogen bonding, they tend to glom together. But anyway, H+, H3O. So a base then, according to Arrhenius, is a substance that, when dissolved in water, increases the concentration of hydroxide ion, or OH negative. So the Arrhenius concept is a little bit, it's very limited. It only looks at acids and bases in aqueous solutions only. And we also, it's kind of hard to tell sometimes. For example, NH3 is a base. And when you first look at that, you think, well, how is that a base? Well, actually, if we put NH3 in water, and we'll talk about it in the next section, what happens is you get NH4 plus OH negative. So OH is produced. So it is an Arrhenius base in that way, but it's hard to tell sometimes. Also, like I said, it's only in aqueous solutions. And actually, we can have bases that do other things. So OH isn't the only kind of base, and we don't always have to have OH produced. So anyway, a much better concept is called the Bronsted-Lowry. So that's what we're going to talk about next. So according to a Bronsted-Lowry concept of acids and bases, an acid, and this is the definition you'll probably want to remember, an acid is called a proton donor. Proton donor. So what happens, an acid-base reaction is where, and let me just start out by saying proton is H+. So technically, so when we're talking acids and bases, when we say proton, I mean, literally it is. It's a proton because hydrogen has only one proton and one electron. And if you remove the electron to make it positive, then it really literally is a proton. But it's not in the same way. It's being transferred from one thing to another. So we call it a proton donor. And then a base is called the proton acceptor. Proton acceptor. So an acid is a proton donor. Base is a proton acceptor, and an acid-base reaction is when a hydrogen is transferred from the acid to the base. So when we consider an acid-base reaction, because they tend to be in equilibrium, both the forward and reverse reactions will involve a proton transfer. So that means we have an acid and base on both sides of the equation. So let's look at the next slide and you'll see what I mean. Okay, so this is what I wrote earlier. So consider this reaction of NH3 and H2O. NH3 plus H2O gives us NH4 plus and OH negative. So in this way, we said earlier NH3 can act like a Arrhenius base because it does produce OH negative, but on a broader sense, NH3 acts like a base because it actually accepts a proton. So if you look here, what's happening, you can literally see that H2O gives up an H+. The H+ is transferred to the NH3, so now it becomes NH4+, because it's gained an H+. And now the H2O has lost an H+, so it becomes OH negative. So H2O is considered an acid, and NH3 is considered a base, and there is a proton transfer. And this is looking at the forward reaction. If we look at the reverse reaction, because this does tend to be in equilibrium, looking in the reverse direction, you can see that NH4 plus transfers a hydrogen to the OH negative, so the OH negative becomes H2O, and NH4 plus becomes NH3. So in the reverse reaction, NH4 plus is called the acid, acting like an acid, and the OH negative is a base because it's accepting an H plus, NH4 plus is giving up an H plus. So we have acids and bases on both sides of the equation. And when you look, so NH3 is the base, NH4 plus is the acid. They are called conjugates of each other. They are a conjugate acid-base pair. And a conjugate acid-base pair are a pair of compounds that only differ by an H+. So in this case, NH3 is the base, and then NH4 plus, which has gained the H+, is now the acid. So they are acid-base pairs, and of course then, okay, so just what I said, conjugate acid-base pair consists of two species in an acid-base reaction, one acid and one base, that differ by the loss or gain of a proton. So they're only differ by an H+. So in the same sense, so NH3 and NH4 plus are conjugates of each other, and in the same sense, H2O and OH negative are conjugates of each other. H2O is the acid because it has the extra H+. OH negative is the base because it's missing the H+. So they are conjugates of each other. So we have conjugate acid-base pair. Base acid. So notice you always have to have an acid and a base on each side, and an acid and a base on each side, and the conjugates are just the only difference is the H plus, because so the H plus has moved from here to here, and in the process NH4 has gained the H plus, OH, H2O has lost it to become OH negative. So notice, I know some of you are thinking, wait a minute, how is acid a water? I'm sorry, how is water an acid? Well, it's an acid because of its function. What is it doing? It's donating an H+. So Brown-Stellari defines a species as an acid and base according to its function in the reaction. So actually H2O can also act like a base, as we'll see in a little while. So again, just one more, just acid-base pair, H2O becomes OH negative because it has given up an H+. So this is the acid and this is the conjugate base. And then the base has gained an H+, so it's gone from being a base to a conjugate acid. And so again, these are conjugate acid-base pairs. Okay, so let's do a few examples. You might want to pause the video for a minute and figure it out for yourself, and then replay it and see what the answers are. So determine the conjugate acid-base pairs in the following reaction. So a lot of times you can't tell, you have to do it by inspection. Again, take a pause, see if you can figure out what they are, and then come back. In this case, so notice that HCl and H2O both have an H, and we've seen that they both can give up H's. It just depends on the situation. So by inspection, we see that the HCl has given up the H+. So in this case, it's an acid because it's a proton donor, and so this is the conjugate base. H2O plus H2O has gained an H+, so it's a base. And this is the conjugate acid. And so the proton has left the acid and gone to the base. It's transferred from HCl to H2O+. And what we'll see later is we'll be able to predict this because it depends on which acid is stronger, which one's more likely to give up the H+. So it's kind of like a tug of war for the H+, who wants it more. Anyway, let's look at the second example. Looks very similar. The H2O has gained the H+, so again, the H2O is the base, and this is the conjugate acid. And so therefore HNO2 must be the acid, and in fact it's given up the H+, and so it's the conjugate base. Depending on which way you're looking at, they're conjugates of each other. I mean, there's nothing specific saying this is the acid and this is the conjugate base. If you were looking at NO2 negative as the base, then HNO2 would be the conjugate of it. So they're conjugates of each other. Okay, then finally, again, the transfer has been from the H+ has transferred from the HNO2 to the H2O. Okay, and then finally, in this case, the HF is the one giving up the H+, so it's the acid, and this is the conjugate base. And that means that HCO3 negative, even though it's an ion, it can gain a hydrogen. So it's a base, and this is the conjugate acid. You're always going to have one acid and one base on every. So this time the H is transferring in that direction. All right, and there you have the answers. All right, so how do you find the conjugate acid or base? So like I said, they're conjugates of each other, and they only differ by an H+. So if you have a base and you want to find the conjugate acid, what do you need to do? You need to add an H+. So you have to increase the number of H's by 1, and you have to increase the charge by 1. So again, you might want to pause this and see if you can come up with the conjugate acids of these, and then you can restart it and check yourself. Okay, so H2PO4, if we're going to add an H, then it becomes H3PO4. And if the charge goes up by 1, if it's a -1 now, it becomes 0, so there's no charge. OH negative, most of the time, so let me just kind of back up. Most of the time we're going to add the H to the front. OH negative is just going to be one of those exceptions that you're going to have to remember, that if you take the H away from water, you're going to get OH negative. They kind of change places, but usually we write it as H2O. So again, the negative charge has become neutral, and we've added an H. Cl negative becomes HCl, neutral. HCO3 negative becomes H2CO3, again neutral because that's -1. Okay, how about this? CO3 -2. So we just add one H, HCO3, and because it's a -2, if it increases its charge, now it's -1. So notice that HCO3 negative is the conjugate acid of CO3 -2. All right, what is the conjugate acid of H2O? Well, we have to increase the number of H's by 1 and increase the charge by 1. So now, because it's neutral, it's gone up to +1. NH3, same thing. And this is another one of those weird exceptions. You wouldn't really write it HNH3, although you could, because really only one of the H's, this H is acidic. But anyway, we increase the number of H's by 1 and we increase the charge by 1. So here's the answers that I just went through. All right, so then if you have an acid and you want to find out what is the conjugate base, this time you're removing an H+. So again, don't forget, you decrease the number of H's by 1, but you also have to decrease the charge by 1. So if you have H2O, which is neutral, and you want to remove an H+, it becomes OH negative. Again, that's one of the ones you just have to remember, that the H switches places. HF becomes F negative because it's neutral, it's becoming -1. H2S, you're just going to remove one of them, and so it's a -1. You can actually, what we'll talk about in a little while is if you've got more than one H in the front, you can actually lose them sequentially. So actually the conjugate base of HS negative would be S -2 because you'd remove another H and it would go down by one more, so -2. H2PO4 negative would become HPO4 negative 2 because we're decreasing, so -1 to -2. And then, like I said, if you want to take it off again, take the next H off, then you have PO4 -3. So that's the conjugate base of HPO4 -2. H2PO4 negative becomes HPO4, and actually we actually can have H3PO4 as one acid, and so this is H2PO4 negative would be the conjugate base of H3PO4. So we can actually remove 3 hydrogens in sequence. Okay, HCO3 negative, again, because we're trying to find the conjugate base, it will become CO3 -2. Now you might notice that actually H2CO3 is an acid, and so the HCO3 negative is the conjugate base of H2CO3, and then we can remove a second one, and we'll talk about that more in a little while. So these are just the answers. All right, so obviously you've already noticed that some species can act like an acid or a base because it's just function, what they're actually doing. And like I said earlier, it's kind of like a tug of war. Who wants the hydrogen more? So different things can act differently depending on what they're reacting with. And so a species that can act as an acid or a base is called amphoteric. Sort of see that the prefix ampho, like amphibian, can be both water and land. So similar, they can act as either an acid or a base. So in other words, they can gain or lose a proton. We saw obviously water is is a very amphoteric species. It can gain an H to become H3O plus. It can lose an H to become OH negative. And we saw just on the previous slide, HCO3 negative is also amphoteric, because here you can see that I can't find my pen. Oops. Okay. Where am I? Okay, there. So now you can see that HCO3 negative can donate a proton to OH negative to become CO3 negative 2. So here it's acting like an acid because it's donating a proton. But in a different situation, we saw this one earlier. In this case, the HF is much more likely to give up the hydrogen to the HCO3. So now it's acting like a base. So it can, and we kind of saw so that a lot of those things that have more than one hydrogen. So HCO3 negative, HPO4 negative 2, H2PO4 negative, a lot of those can be amphoteric. Again, water, the amphoteric characteristic of water is very important in aqueous solutions. So we can see here H2O can act like an acid, in which case it donates a proton to become OH negative, or it can gain a hydrogen, so HF donates the hydrogen to H2O, and so now water acts like a base. So very important property of water. So you've probably noticed that in Bronsted-Lowry, a base then is just a species that accepts protons, and OH negative falls into this category because it's definitely a base. So, you know, in the Arrhenius, we really only focused on the OH negative. Now we can see that many things can be bases, even besides OH negative. We can see that acids and bases can be ionic or neutral. So, you know, OH negative can act like a base, H3O plus can act like an acid, HCO3 negative can act like an acid or a base, so they don't have to, so they can be ions. In reality, they're not restricted to aqueous solutions, so you don't have to have water involved in the reaction at all, and you can still have acids and bases. And like we said earlier, some species can act as either an acid or a base depending on the other reactant. So this is just a term that we're going to use a lot in this chapter, acid ionization. When an acid reacts with water, we call it the acid ionization of water. We know that water acts like a base in this case, and so the H will donate a H plus to become H3O plus, and then the conjugate base of the acid is left over. So this is ionization when an acid reacts with water to give H3O plus and a conjugate base. It's called acid ionization. And in the same way, we can have base ionization. So when a Bronsted-Lowry base reacts with water, we call it base ionization. In this case, water acts like an acid, so it donates the H plus to the base. The base gains the hydrogen, and then we have OH negative, the conjugate base of acid. We're going to look later in this chapter at a lot of acid-base ionization reactions and problems.